Welcome to a lesson with Dr. Powell. Let's take a look at how we can conceptually think about what it means for a matrix function, a linear transformation like this one right here, described by this matrix under a column interpretation, what it means to have a right inverse, and visualize kind of what's going on and even utilize it. So first, how do we come up with the right inverse? We look at a column operations matrix, like to get Smith normal form. How do we get this column operations matrix? By doing column operations here and do the same ones to an identity matrix. Okay. And you can kind of see kind of what happens. You have an identity matrix like here, like what are you doing? Taking -1 times this column, you're adding it to that one. And that's kind of what happens in these first two columns. And then we're just going to be changing this. And if this is already changed to a 0 right over here, that would be like -2 times that guy and -1 times that, and kind of doing that. So 2 times this, bringing it over, -2 times this, bringing it over would be a -2, a +2, but then you're going to be subtracting 1, makes that a 1 right there. Anyhow, we get this column operations matrix. Now, from this column operations matrix, we can split it up into two parts. All right. The part right here that corresponds to the zeros actually represents the kernel of f. Great. Then the other two guys actually give us our right inverse. Now, we're thinking column interpretation. The actual columns in here make up the range of the right inverse. We're going to call the right inverse G. In fact, you could even think this right here as a matrix is G. Okay. And so, of course, the two columns you see would be like the range. This guy would be like the kernel of f, or the span of this vector is the kernel, and the span of these two vectors is the range. So span of these two guys gives us a plane, and this guy gives us a line. And this would be the origin right there where they intersect. Okay, so you can kind of think about this. Now, notice I use this fancy symbol right here. That's just to describe that if you take a basis of on this straight line and a basis of the plane and put them together, you get a basis for all of R3. That's all that symbol means. You combine the bases and you get the basis of the whole thing. That every vector in the basis of this guy is linearly independent to that one. And that should make sense because this column operations matrix is an isomorphism, meaning that the columns themselves are linearly independent to each other. Okay, so, so even from the column operations matrix, we see kind of a nice visualization of something going on between a function and its right inverse. But we can go do a little bit more. Let's take a look at this a little further. So what if we just take any vector in R3 at all, like v here, as I described, so a vector coming out here, and think about components. Let's think about a component that's parallel to the kernel of f. All right, the kernel of f is a line, and let's just take a vector parallel to it that comes along right here, right? All right, a vector that's parallel to it, and then let's suppose that it's a vector parallel to it that takes us down to the plane described by the range of G, okay, which is this plane right here. So a vector that's parallel to that, you take it and then you go on like this right here. And you notice that V itself can be described as the sum of VK plus VP, VP being something parallel to the plane, and VK something that's parallel to the kernel right here. So we can decompose V. Actually, this decomposition is pretty unique, and that's to deal with the fact that kernel of f, right, and the plane of G right here, they're linearly independent to each other. So they make up a coordinate system, a nice coordinate system. There's one and only one way of describing any vector v. So one thing coming from this axis and the other thing coming from that plane uniquely, that'll add up to v, because there's only one unique representation in coordinates that gets you v, because we had that idea of it being linearly independent to each other. All right. because that column operations matrix was an isomorphism, and columns were linearly independent to each other. That's really where it came from. So yeah, so V can uniquely even be written. This is a unique representation, a unique vector that's parallel to the kernel, and that's in the plane, and those added together make V. So we can actually find what these vectors are, this VK and VP. Now, how do you find this? Well, we're going to focus on how to find VP. Okay. How do you find VP? And we have a little formula for this. Now, this is a little interesting because you think about it. If we take, remember what G is? G is a right inverse. What does it mean to be a right inverse? That means that f of G, G on the right side here in the composition, or even with matrix multiplication, under the column interpretation does this as well. If you put the matrix for G on this side of F, you should get the identity matrix. All right, so this should be the identity function. All right, but you see what we're doing here? We're swapping them. We're doing G of F. So we're putting the right inverse on the left. And if we do that, and we run a vector into it, we actually get something interesting. We get this VP guy. Okay, that's actually how you find your VP. It's by switching the order of these guys and putting it. Now you can kind of see that a little bit, why that might be true, at least computationally here. So, for instance, if you end up taking, so if you take F and let's just consider, okay, so let's compare the images of F of, yeah, so let's compare the images of F of V and F of VP. Okay, let's compare these two guys. So F of V and F of VP. Okay, let's just kind of look at those for a minute. If we think of VP as being this guy G of F of V, all right. So let's just replace this right here for G of F of V for VP right there in what I wrote. Okay, let's just do that. Just think about this for a minute. So I have G of F, okay, of V. You think of it, so let's think of it that way. Now notice, and in fact, we can even put a composition symbol right here. You can use the fact that G is a right inverse to notice that that's the identity. Meaning, oh my goodness, these two guys are the same. F of V is the same thing as F of G of F of V. So if we label VP as being this, oh, how does that help? Well, you notice that if you so you notice if you subtract these two guys, you're going to get the zero vector, right? Well, that means if we factor the F out of both of those guys, F of V minus, and that's G of F of V, notice that we labeled this as our VP, right? Well, that should make sense because what this says is that F of V minus VP is equal to the zero vector, meaning that V minus VP is in the kernel. Ooh. Well, okay, so if we just say that V minus VP is VK, so let's just define VK as being V minus VP, because we know that's in the kernel. But you notice if you just add VK, which is this, plus VP, cancellation, you get V. Well, there you go. And remember how we said that was unique. It was a unique way of doing it. Well, this is a very unique way of doing it. So all we need to do is find VP, which is just done by this, putting G on the left side instead of the right. So we find our VP, and then we can just find VK just by simply subtraction or seeing what's left over. I mean, let's take a look at this right here. Let's look at 1, 0, -1. Notice how I already have this split up into two component parts, one in the plane of G and the other one in parallel to the kernel of F. So how did we find this VP? Just simply by running this G of F DIL. So let's take a look at that and see if we can compute that. So G is here. Okay. So we have 1, 0, -1, 1, 0, 0. And F is right here. So we have 1, 0, 2, 1, 1, 1. And then over here we have, okay, so we want to plug in v into that. That's 1, 0, -1. So we have 1, 0, -1. So we plug that into this. All right. And as we do so, we can kind of think, okay, so column interpretation, I'll just take 1 times that column, 0 times that one, -1 times that one. So we have 1, 1 minus 2, 1. So you end up getting what, -1, 0. And then you plug that into this matrix right here. So which means just take -1 times that first column. So you end up just getting a 1, see, a -1, 1, 0 output. All right. So we just ran v into g of f, and you ended up getting this, which we're going to call our VP. All right. So let's take a look at that. So -1, 1, 0, that's our VP. So how do you find the rest? We'll just say, well, what do I have to add to this to get that? And that's what your VK is. You think -1 plus what is 1? Well, just a 2. 1 plus what is 0? That's -1. 0 plus what is -1? Just a -1. Oh my goodness. So we get our VK, we get our VP. And all we have to do to get this decomposition is just think the reverse of what G was doing as an inverse. So put it on the other side, and or as a right inverse, and now you put it on the other side, so it doesn't invert it, but instead what it gives you is it gives you this projection. So you got that projection, and then you just kind of fill it in. What do you have to add to that to get to there? And this is the unique decomposition, the projected onto the plane, at least via a component that's parallel to this line right here. Now, right here, so remember, the line was determined by this guy in the column operations matrix, and the plane was determined by this part of this column operations matrix. Now let's suppose we have a particular line and a particular plane that we want to work with. We can make a column operations matrix, then based off of that, we actually have our matrix G, and then to find a matrix F that would correspond to this, then you just find the left inverse of that matrix, and then we're on our way. So we really can use this technique to get any to decompose any vector according to projections that we would like. And we don't even have to use planes and lines. We can expand this to multi-dimensions and use the same technique across any kernel and some kind of higher dimensional plane. Thanks for watching.